as I just said, I'm not going to talk about IRAX or SKO, although I'm going to mention SKO, but I'm going to talk about cosmology and redshift surveys, as we do mostly in optical astronomy. And that will be the outline of my presentation. I will do, because you're not maybe familiar with cosmology, a brief history of cosmology. This is essentially based on the work that one of my PhD students done, Jashi Yu, who's basically presenting. I've passed the private defense and is going to present in December. And so in there, we're going to see a part of the historical perspective. So going back 100 years ago, of the first development of cosmology, and then on the work she's been doing on modeling in the galaxy distribution. Although this is very focused on the galaxy redshift survey, maybe there's something interesting to be adapted for IRAX, for example. And then I'm going to talk on the next project that we are working at EPFL, next project in terms of galaxy redshift survey. And because these, need some new technology development, and that's something EPFL is quite good at trying to push technology. And then I finish by some work I've been doing with Sarah Cannondine about exhibition about cosmology and the universe. And then I give you some tips about collaboration between Switzerland and South Africa. So I don't know how much you're all familiar or not about cosmology. Basically, we have this picture of the universe where basically you have the timeline, and you have the start of the universe with the Big Bang, and over there it's where we are. And there's different periods in time that basically have been discovered through history, through 100 years of thinking and wondering about the universe. And so we've been classifying them in different moments. The Big Bang moment, which basically try to explain the early universe. The dark area with the first light, which you will see, it's the first time when we start to try to understand what's the universe and how it expands. And then we have the matter-dominated area, and then the lambda-dominated area, and then maybe today is the area of dark energy, because it's what we try to understand these days in cosmology. So those moments, those areas in time, are both area in time in the universe, but they're also, interestingly, time in the human development and understanding of cosmology. So I'm going to go through this. So the beginning of cosmology is basically 1915 with Einstein equations of the universe, which is captured in what we call the general relativity theory. And the key equation in that theory is this very weird equation. If you're not a mathematician, you think, oh, what does this all means? But basically, it's very simple, in fact. Let me describe what you have. On this side, you have a description of the geometry of the universe. So it's with two indices, because basically you are capturing both time and space in the geometry of the universe. And then you have this lambda, which is this cosmological constant that was added into the equation to make a steady state universe. But now we realize it's a different value, and it could explain the accelerated expansion of the universe. So here, geometry of the universe. On the other side, you have G, the gravitational constant, and you have this tensor, T mu nu. And basically, T mu nu represents the content of stuff in the universe, whether it's matter, whether it's radiation, whether there's other component, right? But essentially, it's where you put the mass and energy in the universe. It's how it's described in T mu nu. So basically, geometry of the universe reacts to the content of the universe. And that's basically the theory of general relativity. relativity. And so from this equation, and when you put a bit other parameter or the constraint in like the geometry of the universe or of its representation, you come down with the same equation into this equation here. Okay, they're just the same. You just put more knowledge into the equation, and that's give you this. And so what we have here is a description. H of z is basically how the universe is expanding, because from that equation you can show that it's either expand or contract, but there's very little changes, just a steady state universe. And you see that the expansion of the universe is controlled by a number of parameters. These omega lambda, omega k, omega m, omega r. So you have lambda, which is just this cosmological constant. K is describe the curvature of the universe. M describe the matter content in the universe. R content describe the radiation in the universe. So basically photons and neutrinos. So you have this value, and then you can show that basically you have an expansion of the universe. That's the most likely thing that happened, and that's have been measured, in the 1930s. And then you have all these Einstein the universe, which is kind of a spatial universe, and that was favored around the 1930s when we just realized that the universe was expanding. Of course, that's just a model, because that model just gives you some values for these omega n, omega k, omega lambda. But in fact, at that time, we didn't know the values, right? That was, well, if we keep that model, this Einstein de Sitter model, then that should be those values. But of course, nobody at that time could measure anything. So there was kind of a supposition. So, the theory was laid out, but then, you need observations. And the first observation about cosmology came with the first light. What I call the first light is the first light coming from the very early universe, what we now call the cosmic microwave background. So that's something you measure in microwave. Typically, the peak of the emission is at 1-2 millimeter, but you can also detect it in radio bands. And basically, in 1965, 1966, there was measured in radio of this microwave background, cosmic microwave background. And from that 2 points of measurement, and the fact that you see all over the sky, you say, well, it's a black body curve, probably black body emission, and then you can derive the temperature of this black body. Of course, with 2 points, it's a bit of a challenge, but there has been after more data points that confirm this black body at 3 Kelvin. So how can you have a universe radiating at 3 Kelvin? Well, because it was very hot, and because of the expansion, the temperature has been cooling. So the temperature at that time was 3000 Kelvin, and it cooled by a factor 1000, and that's why we're measuring at 3 Kelvin. And from this picture, you can say, well, my universe has been expanding, okay, by thousands of times. And of course, if the universe has expanded, the density of radiation and density of matter has been decreasing as a function of time. And so today we're here, that's the typical size of the universe. And before the temperature was much higher, and of course the size of the universe also was much smaller back in time. So when people discover that, then they try to see, okay, but that's one part of the universe, but there's still a lot of questions to answer. Is the universe uniform? Is it clumpy at the beginning? Is it really the Big Bang theory is correct? Or do we need a steady state universe? Steady state would mean like I would create matter as the universe is expanding. Do we have a hierarchical or top-down growth? So to answer that, people have started to look at the spatial distribution of galaxies. And and it's also the time by the end of 1960s that you discover dark matter in the universe. You realize that mass around the galaxy is much more important than the mass of stars. Okay, and so you start to have this ingredient, the dark matter, in your cosmological model at that time. So then people start to say, oh, but how much dark matter, right? And so people have been looking at, you know, how much matter, omega n, you can have in the universe. So if you have a visible mass, at most you go to 0.1 from stars and gas. And the invisible mass, the dark matter, you know, will put you something between 0.3 and 1 in terms of omega value. The galaxy clustering measurement was not really helping in determining this number. So there's been other techniques to try to pin down that number. And it's at that time also we start to have very massive redshift surveys in the 1980s. And then we detect that the distribution of galaxy was not at all homogeneous. There was some kind of walls, empty voids, features in the distribution of the galaxies. And that's a measurement in the 86, sorry. And this is a measurement that was done 10 years later, and you really see appearing this structure of the galaxy distribution. So, of course, you know, it was relatively easy to model the dark matter into simulation. That's what we call n-body simulation. Particles of dark matter don't interact. So it's very easy to put that in a computer and make a simulation. You know, although it's still a lot of computation, it's very easy. But of course, you know, it's not only dark matter in the universe, there is galaxy. And so question is how you make the link between dark matter and galaxies. So people have been simplifying this, you know, the dark matter distribution, you can think there in the end halos of matter. And then in the halos, you want to put the galaxies. I mean, the galaxies that I put in blue. But of course, if you have 2 galaxies or 4 galaxies nearby, they will merge together. They will not only form stars, but then they will become red galaxies. So there's trying to develop this relation between galaxy and dark matter. And that started basically, you know, in 1970s. There's been a big question between 1970 and 2000 of what is the various components of the universe. What are these omegas? Okay, on one side, you have like the standard cosmology model with no extra component, which is consistent with the Big Bang temperature. And then there was galaxy studies that say, oh, more and more those galaxy studies were showing that omega m was certainly larger than 0.5. That has consequences also on the value of the Hubble constant. If you have, in this case, you want a high value of the Hubble constant. If you are in this standard model, then you know omega n equals 1, and you need to have h naught to be 50. So there's been a debate at this time. You know, what is the different? What is the model? Do we have a standard cosmology with omega equal 1, or do we have a unstandard model with omega less than 1, less than 0.5? But that means that you have this cosmological constant in the universe, which we don't really understand. So there's been a lot of measurement, and in part there has been measurement from the supernova as standard candle that show basically that you have effectively an omega lambda value. It's a non-zero one, and it's basically if you think the universe is flat, then it will give you omega value of 0.3, omega m value of 0.3, and omega lambda of 0.7. And what does mean? It's that the universe is accelerating. So this is very counterintuitive because, you know, if you think there's a lot of matter in the universe, matter try to pull things together. So they should basically at some point stop the expansion of the universe. But with this measurement, we find the contrary, that the expansion of the universe, it's accelerating. So then there's how you explain this acceleration. And so, well, I think we still don't know. It can be, this dark energy component, but that could be also change in the gravity model. So what also happened starting in 2000 is that we start to make very precise measurement of these parameters. And the first precise measurement came from satellite that observed the CMB and who could make this measurement of the anisotropy of the distribution in the CMB very, very accurate, right? We have measurement below the percent level of this curve, and in this curve is encoded a lot of the parameters. That was back in the 1990s. You see, we had data points with huge error bars, and the theory was this line. Okay, so you could put any theory through your data point. And nowadays, we have satellite data. I mean, this measurement is from Planck in 2018, where you have very, very tiny data point with very, very small error, and you don't have much freedom in terms of your model parameters. So you get to better than 1% precision for all these parameters from just the CMB observation. And that basically tells you we are in the lambda CDM type of cosmology. Although if you try to not go with a lambda parameter, but with a dark energy model, a dark energy model will come with two parameters, W0 and WA. And here, so lambda model will be this point. But what are the data telling you is that, well, it could be any point in this region, right? So we need to develop observation that will tell you, where we are, what type of WA, what type of W0 our model of the universe sits. Right? So until very recently, in fact, all the models were pointing to a lambda model where W0 equals -1 and WA equals 0. So what has been the very much transformation in the recent years is this observation of dark energy using what we call the baryonic acoustic oscillations. So where these oscillations are coming from? They come from the CMB data. If you go back to this curve, that's fluctuation, that's basically the power spectrum, the fluctuation that you see in the CMB data. And there's a particular scale here of fluctuation in the CMB data. So that's a fluctuation in temperature, but in fact, that's also fluctuation in density, right? And this fluctuation in density will propagate as the universe expands. So if you're able to measure this fluctuation, this peak, not at the CMB time, but in the galaxy distribution, it's basically a way to measure the expansion of the universe. And that's basically what I want to show here. You could see this size, this scale of the fluctuation you see in the CMB data as something you can measure in the distribution of galaxies. And this scale will tell you whether you are in this type of model with dark energy or you are this type of model with no dark energy, but only dark matter and baryonic matter. And this scale is basically fluctuation you can see in the galaxy distribution. But of course, to measure that, you need to have a lot of galaxies. Basically, if you want to have just one measurement, you need at least 10,000 galaxies. But if you want to make this measurement across the sky and a function of redshift, you tend to have like millions of measurements of galaxies, right? So there's been a lot of work, in particular with the Sloan Digital Sky Survey, to survey the galaxy redshift distribution. And that experiment over 20 years of observation collected 4 million of redshift of galaxies. Okay, 20 years. And the technology they were using was this fiber system, where people by hand were putting optical fibers into plates, where position of the hole were basically the position of one galaxy in the sky in a particular direction of the sky. So we made, you have just a view here, very clear, but we had to do more than 10,000 plates of like 1 meter diameter and with 1,000 holes in each of these plates to be able to measure 4 million galaxy redshift. So I guess if you've done that after 20 years, if you want to continue, you want to do it differently, right? So that's also the challenge. So this measurement done with the Sloan data basically been able to measure the BAO peak. So that's the galaxy correlation function. And in the galaxy correlation function at about 100 megaparsec, you see this blip, which is the BAO peak. And you can measure it at low redshift, 0.3. There was the first measurement back in 2005. And you can measure up to redshift 2.3, which is in the galaxy, in the quasar distribution on the sky. And that was a measurement done in 2013, but there's been even better measurement later on. So you move from low redshift to high redshift. You can do precise measurements if you also reconstruct the galaxy position. Here is the idea is that because of the velocity of galaxies, your BAO peak will be smoothed out because each galaxy is moving in the universe. So you can, and they're moving because the mass distribution is not homogeneous, but you can reconstruct this movement and remove this movement, and then you have a reconstruction of your density field, and then you measure much better the BAO function and the BAO peak. The BAO peak is not just a one-dimension parameter, it's a two-dimension parameter, because first you see along the line of sight, you can measure your BAO peak along the line of sight. If you just look at distribution of galaxy along the line of sight, or you can measure your BAO peak on the sky, because your BAO peak will be also imprinted across your sky. So you have two measurements, the redshift measurement and the angular measurement. So if you combine these two, you also improve your measurement of your BAO peak. And that was basically the result that came out from the Sloan survey. And what we picture in this image is like the CMB lines, okay? And that's give you the size of the observable universe. And each data point you see here is one galaxy redshift measurement with different colors because we use different tracer, whether those are red galaxy, blue galaxy, quasars, and they span basically from redshift 0 to redshift like 3. So you go up to 11 billion years back in time. But you see there's still information in this plot that you don't have. Basically between 11 gigayears to 13.5. That's where you still have galaxies, but behind 13.5 to 13.8, the only measurement you could get in the future is through H1, so using, for example, SK or NWA today. Okay, and what you see here, it's for each of the tracer, you have the measurement of this BAO peak. And all these measurements of up to 2020 confirm the accelerated expansion of the universe, the need to have a lambda, but not to have something different than lambda. So as we moved on, we are in 2024, and we basically starting to have a new measurement of the galaxy distribution. And what we do now, we do that with robots. We replace the fibers that people were putting in and onto the optical plane with robots. And that's the focal plane of the DAISY experiment, of where you have 5,000 of these robots. And that's kind of a closed loop of some robots for another experiment, for the Sloan experiment, but that works similarly. And you see how they move, right? And then they can, let me move them again. So like the yellow thing is the fiber, right? And the robots move the fibers onto a small, what we call parallel field. And so any point on your parallel field can be accessed with your fibers, and then you collect the light of the object, which is at the position of your fibers. Of course, you need to be super precise because a fiber diameter is 100 micron, and you want to adjust the position to your fiber to your object to typically better than 5 micron. Okay, your air is 100 micron, so that gives you the the size of the thing. Okay, so
like a spider. It looks like a spider.
Yes.
It doesn't help that you have 8.
So you have to be super precise, when you do these things. Okay, and so the DAISY project started back in 2009. It went into the telescope in 2019. There's been commissioning, and then there's been COVID. And then really, like only in December 2020, the survey started with target selection validation, 1% of the survey. And now we have data around the DAISY collaboration for the first year. And soon, in the coming months or so, we're going to have the data for the first 3 years. In just 1 year, this project has collected 14 million redshifts. So more than 3 times that what's collected in the last 20 years. So you see the increase of the data coming from these surveys. And that's give you the first year data collection onto the sky. So ultimately, every part of the sky will be seen a few times, so 5 or 6 times. So that's why it's in red. When it's blue, it's just there's been just 1 visit of the telescope. And ultimately, you're gonna cover more than 14,000 square degree of data. So 1/3 typically of the sky. And the survey is progressing very well. By end of this year, typically we will have conducted 5 years of survey already because we are getting advanced, and this will continue. So I think today we are probably close to 40 million redshift measurements, ultimately, this experiment might reach maybe close to 100 million, maybe not 100 million, but close to that number in 5 years' time from now. Okay, now you collect the data. What you do with your data, you want to compare it to your theory. So that's the data set being collected, different tracers. Low redshift tracers, then red galaxy, then emission galaxy, and then quasars. Those things are quasars. And so basically you go up to redshift 3. This part is very low density though, but still you can do a measurement. And what you want to do is do this BO peak measurement at different redshift. And so you're basically observing your correlation function, but you want to compare it to theory, right? And so question is how you compute the correlation function from your theory. And when you do then this comparison, then you can deduce your cosmological parameters. And then I talk a little bit more after on those cosmological parameters. Of course, you have a lot of systematics to take into account. And in fact, more data you get, more you're sensitive to systematics because your statistical noise gets smaller and smaller. And what's come in your data is essentially systematics. And you have basically to deal with all your systematics. You have systematics because your coverage is not uniform. You have systematics because, well, it's not only not uniform in coverage, but also in density. And also you may have collisions of fibers. There's places you cannot observe because otherwise your fibers will collide. So that you have also to take into account that. And then in terms of your measurement, a galaxy spectra is basically a 1D information which is noisy, and you have you have a sky noise that you need to remove, and your signal, what you're looking for, might be just a signal from the sky, I mean from the atmosphere, but not from the galaxy. So you have to distinguish between those various nodes, and you have to take in good control of all these systematics before you're able to go to your video peak measurement. I will not go into details to that because we could spend the day on that. What I want to explain a little bit, because there's been quite an active development we did with JSU, is how we mock up the universe and how we model this galaxy halo radiation, right? So we start basically from dark matter distribution, and in this dark matter distribution, we want to paint galaxies in that simulations. Okay, and so how we do the painting of the galaxy there. So we want to define massive halo here, and then for the massive halo, dark matter halo, you want to see whether you put galaxy in this halo. And so you also can question how many galaxies are put in one halo, depending on the mass of the halo. And also you want to link the properties of your stellar mass to the halo mass, and you know, how we compute that. So one way, there's two different ways to do that. Either you do that with a galaxy halo model, or you use this sub-halo abundance matching, and that we've been focusing on this methodology. So you have your N-body simulation. Just that's the concept of this SHAN. Okay, you have this galaxy halo distribution from your galaxy, and from observation, you can also have you know, luminosity function of your galaxy, right? And so you know how many bright galaxies there is, how many faint galaxies there is in the universe, and so you're gonna attribute each of the galaxy in your catalog derived from your galaxy luminosity function into a sub-halo of your data. Okay, and of course the brightest galaxy will go in the biggest halo. That's, you know, that would be the sensible way to do, right? And of course at some point you run out of galaxies, or you're not sensitive enough to put a faint galaxy, so you would cut, right? And that's basically you observed number density of galaxies in the universe. So you cannot go to very tiny halo because in the data in your galaxy observation, they don't appear. Okay, so that's how you do the ranking. And of course, you do that, you rank your halo in your simulation, you rank your galaxy halo in your galaxy observation, and you match that, and that you produce a mock universe. That's the simple way. But of course, what's tricky is your tracer, whether it's emission line galaxy, red galaxy, so with no star formation, or whether it's quasars, then you have to adjust. Because, for example, when you define your galaxy catalog, you tend to also, for example, don't observe the brightest galaxies because there's not informative, because there's not so many. So you would put like a cut on the brightest galaxy you're gonna observe. So they will not be in your catalog. So that means you need to define also the sail function depending on your target selection, meaning that this type of halo who probably host a galaxy, in fact, you don't observe them. And that's typical galaxy at the center of a cluster. Those very massive galaxy at the center of a cluster, usually they don't end up in the catalog of these redshift survey. So you have to have this sailing, okay, because when you do this matching, because basically you don't observe this thing. So you have to remove them.
So is that observational artifact?
Yeah, that's purely observational.
Yeah, okay.
It's due to the way you target your galaxy in your redshift survey. But of course, you know, so if you're just interested in the galaxy dark matter connection, then of course you need to have that, right? But because you want to be very close to your data, to your observation, you have to take into account this sailing. So that's one aspect. And this aspect is it's different, of course, for different quasar. Here we have LRG, here we have quasars, here we have star formation. So this particular cut, you know, is more or less important depending on the galaxy you're targeting. So we have this VSAIL parameter to prevent massive subhalo from hosting galaxies. We have also to take off another parameter, which we call vSmear. This is the trying to reproduce the smearing of the galaxy motion. Okay, if you are in a halo, your galaxy is moving in the halo, and that produces a shift in velocity. And so you have to encode this velocity also in your mapping. And this velocity will change whether it's a red galaxy, whether it's a quasar, or whether it's an emission line galaxy. With value very different. LRG is a factor which is less than 100. For quasar, it's more than 100 kilometers per second. And for ELG is less than 10 kilometers per second. And that basically depends of where is your galaxy here? Is it in a big halo or not? And also on the accuracy of the measurement of the redshift.
Why is ELG?
Why?
Why is it the emissions?
ELG, emission line galaxies. So star-forming galaxy, in other words. Okay, and then there's another parameter that we have to account specifically for emission line galaxy is what we call the satellite fraction. How much of these ELG galaxy are not in a main halo, but are in a subhalo? Okay, that's something I didn't, well, I could just go back here. In your n-body simulation, you have a main halo, but then within that main halo, you usually have subhalos. And those subhalos are also hosting galaxies. Usually they're just hosting emission line galaxy, not red galaxy, not whole galaxies. So when you talk about, you know, doing this mapping for the emission line galaxy, you have to take these sub-halo component. Okay, so you have to make sure that your data in the end, when you go from your BAO measurement and to your cosmological measurement is correct. So you have to do a lot of things to make sure that you're not biased in any way. So you have to be sure that your 2-point statistic, that is the clustering measurement, is unbiased. You try to do this reconstruction that I was showing at the beginning to take into account the motion of the galaxy because your galaxy distribution is not homogeneous. You have to be also reliable against cosmic variance, the fact that your density of your galaxy is changing from places to places. We are also been doing blinded tests for the cosmological pipeline. So basically blinding the X and Y axis so that people are not trying to push, you know, towards omega equal matter equals 1 or whatever inconstantly. So people we've been trying to implement this blinded test. And we've been also looking at the systematic control on the theory aspect. And also we looked at the impact from the galaxy halo, the field-usual cosmology, the reconstruction. It's been a lot of work. And in the end, what you end up in this measurement after 1 year of data is that the favorite model is basically not a lambda CDM model, but might be a model with dark energy, with evolving dark energy. And that's it's interesting because it's the first time that the data is showing that. But so you have to be careful because it's the first time. Maybe there's still, bias in the measurement, things that we don't understand in the data. But it's basically are pushing, people to do more. In the sense, we want to learn more. So other project, that's again the timeline I was showing before. There's other projects that are trying to address the same measurements. There's a similar project on the southern hemisphere that will start end of this year. End of next year, which is foremost, which is also a galaxy redshift survey. Euclid, which is a space mission, also try to address the same problem, same question. It has been launched in July 2023. There will be probably a first data release, but very on the small part of the sky next year. But ultimately, they will be trying to do this type of measurement. IRAX is also trying to do some measurement here between Redshift 2 and 3. So opening, pushing a bit in Redshift space. And what I want to mention briefly is the next project in terms of Redshift surveys that are coming up. And that's my own perspective. That after the era of dark energy, that's basically going to finish in 5 years from now, we are going to look at other measurement in the universe, like what was the primordial physics, for example, inflation, and what is the nature of dark matter. That's those questions we can answer with the future survey, and those will start in basically 2030. And for the next maybe 20 years. And there's a number of projects that can access that. And at EPFL, we've been pushing for this for a couple of years now. And just recently, we joined the MUS project, which is a Chinese project to be placed in the middle of Western China on the top of this mountain at 4,350 meter altitude. And they want to build a 6.5 meter telescope. And we are going to provide the robotic system for this telescope. And so just early in July this year, we've been signing a contract with them to join the collaboration, start the collaboration together and promote this project. There's of course other projects. There's a SPEC S5 project, which is basically a continuation of DAISY. And the idea is basically, well, let's take the Mayol telescope and Blanco telescope. One is in Kitt Peak in the northern hemisphere. One is in Chile, southern hemisphere, and populate this new fiber system that we are developing also with them. And so we could have 2 times, so because there's 2 telescopes, 14,000 fibers. So, but like 3 times what's on DAISY, and you could also replace the mirror from a 4 meter mirror to a 6 meter mirror diameter, so you can have more collecting power. And then basically you can do similar as MUST, but of course you do that like 5 years later.
Is it going to be challenging to replace the primary? You'd have to change the whole infrastructure to replace the primary, or
you just replace the primary.
But can it fit in?
So yes,
Okay.
I mean just fit in within the construction.
Okay.
The big fork, right?
Right. Okay.
It's also because you're gonna use like it will be made of not just 1 mirror, but like probably 7 mirrors or 6 mirrors. And so the shape is not totally round, so you can adjust so that it fits the location. But yeah, that's one challenging part. And then there's another project which is called Whitefield Spectroscopic Telescope. That's a European-led project. And the idea is to build a 12.4 meter telescope in Chile. And that telescope would have two instruments, one MOS instrument with at least 20,000 fibers, probably more, and what we call an infrared field spectrograph, which basically each point of your 3x3 arc-minute field of view, you can measure the redshift of any point in this area. But that means you need a lot of spectrograph. We're talking about 144. And this project will be proposed at the European Southern Observatory as the next project after the ELT. But first light tentatively won't be before 2040. So what we're gonna do with this next redshift survey? Well, first we're gonna get even more redshifts. We're talking about minimum 200 million up to 1 billion redshift. So at least a factor of 10 compare what's going to be done by DESI. And of course, that's going to happen between 2030 and 2040, more or less, right? So it's next decade. Okay, and so you have this MUST, you have SPACE-5, you have WC will come probably after 2040. I mean, SKO will also do some redshift survey, but of course, a bit differently. Large number, probably not as many, but it will be also very important because SKO will go also high redshift.
Is that, I mean, I see you didn't put a dot.
Yeah, because.
So is that mid or, I mean, the first stage or the full? Because there's a plan, I mean, the SK original concept was 1 billion galaxy redshift.
Yes,
right?
yeah.
So phase 2 will probably.
Yeah, phase 2 probably gonna, so I don't know, and that's why I just put it without a point, because it's, yeah.
A big,
exactly, there's a big uncertainty.
Yeah.
But certainly it will contribute.
Yeah.
Right? I mean, how much in terms of significance is not clear, but it contributes. So that's a very recent plot we made for the MUST project, and that tells you what type of galaxy you're gonna measure. It's here the co-moving density of those galaxies. So density of galaxy per co-volume. And so they're really comparable in terms of redshift. And so you see that the focus is really to go between redshift 2 and 5 with galaxies. If you were looking at the density of quasars, this is a kind of the maximum density you get from quasars. So you can really have a factor of more than 10 in terms of number density if you target galaxies rather than quasars. But of course, you need a bigger telescope to do that. And that's why people are pushing for 6 meters or even beyond up to 12 meters. Because if you really want to cover high redshift in terms of galaxy redshift, you need a bigger telescope. And so that helps you to basically go in two directions. Go wider on the sky, because at high redshift you have much larger volume available. So that means you can cover this part of the power spectrum, and then you're sensitive on inflation physics. So, what's the origin of inflation, or you know that. And also because you have a very high density of sources, you go to very small scale. And that means you can probe, nature of dark matter. So that's kind of the two new things that this experiment will target. So how you do that? Well, you need new technology, and that's what I was mentioning. We want to provide a positioner system. And in the last 5 years or so, at EPFL, we've been trying to do miniaturization of these robots. So we've been working and placing robots on SDSS telescope, and that's a 22.4 millimeter diameter robot. We've been working on DESI. DESI, it's 10 millimeter robots. And now we're working on robots that are 6 millimeter diameter. That was one of the first, the first development we did was a 7 millimeter prototype, completely built at EPFL. And then we moved to working with companies because they are really skilled, those companies. And we had the first prototype, which was 5.5 millimeter diameter, but it was too fragile. So from that on, we decided to go to what we call a modular solution, where we have a module, and instead to have one positioner, the module have like 63 of them. There's kind of a magic number, why 63, but anyway. And so that's kind of one unit, which would be like maybe 2 kilo, so it can be easily handled also by human. And then you put that, each of the modules into a focal plane, which is this triangular shape, and you cover everything.
So that module contains like these little robots.
Yes.
Okay.
Yes. Yeah. And I'm going to show you more in detail. So that's one prototype module that we have made. And over here you have 6 positioner. I mean, you start with 6 and then you put, up to 63. That's really the first measurement. And you see, you maybe don't see so well, but here there's 6 robots. And they're very tiny. I mean, 6 millimeters is basically smaller than a typical pen, right? And they don't, I mean, they have not to collide because otherwise you'll break them. And this should be super precise because, again, the precision should be at the order of a couple of micron in positioning the fibers. So we have this first prototype running. In fact, we have 2 prototypes from 2 different companies, just to challenge them a bit. And in 2 years from now, we're going to be ready to do the mass production. And the production for like 20,000 of those robots would take like 2 to 3 years, right? So it's basically the time you need to build your telescope and get things ready by 2030 for the observation. Another thing that we're trying to push is, because we have this modular system, is to have also a fully plug and play system. And that means, in particular for the fiber optics, to have very precise low loss connectors, because you want to basically, when you think of these modules, you have electric connectors, but you need also just to be easy to move in and out on your system, to have fiber connectors. But fiber connectors in the market are really designed for telecom, and if they don't care if they lose 5% of the light, but astrophysicists don't lose more than 1% of the light. So we are going to work on this fiber connector system. And that's kind of the preliminary concept we are trying to use. And just to give you an idea, so this is like 1 centimeter on the side, and this is made of glass. And you basically do advanced manufacturing. So with laser to be super precise, so that your position of your hole is within like 1 micron or below. And then you have a real good match between the input fiber and output fibers, and then you don't lose the light. Okay, to finish, sorry, I'm being long, but I want to present also the work we've been doing with Sarah Kendall, so professor at EPFL, about doing science is fine, but also transmitting knowledge to the public is also very important. And so we created, that was COVID time, we had nothing to do, so we decided to create something. And so we created this exhibition, which is called Cosmos Archaeology. It was shown at EPFL pavilions, basically our museum, between September 2022 and February 2023. We had 15,000 visitors, which was quite, a good number. And then we moved just recently in May this year, this exhibition to Shanghai Astronomy Museum. That's like the display. And it started the 18th of May. It's about to finish 17th of November. So it's been 6 months there, about 800 visitors a day. So that's about 150,000 visitors in the end. And so now we have planned to move around this exhibition. So Shanghai Astronomy, then we have a Guangdong Science Museum, probably from January to June. Then we have the National Museum of Beijing from July to maybe October. And then we have the Sydney University Museum from October to December. So this exhibition is basically touring the world. Maybe at some point you can come to South Africa. I think that would be a great idea. Maybe in 2026, because it won't be possible before. And basically, this exhibition is showing about our universe, about our cosmos. It shows with a kinematic sculpture the plates. It also shows the robots that we need to observe the universe. And it's also, show one of the issue of astronomy is the pollution by satellites, and that's kind of critical for SKO and IRAX and all these, because of most of these new satellites in low Earth orbits are telecom satellites, and they produce a lot of radio waves. And also, you have many of these satellites, but most of the stuff orbiting are debris, and those debris could collide with active satellite, and that could create even more debris. So at EPFL, we have a development to try to be more sustainable in space. So we created a company that called Clear Space, who want to go and collect debris in space and destroy them somehow. So that's part of the exhibition. We have also one part of the exhibition is showing Hubble space data. And so people can play with the images. They can see all the database of the Hubble Space Telescope. There's an activity that shows gravitational lensing effect. So people can play and they can go through the universe and put like a lens here and there. And it's very interactive. And we also have like a simulator for the SK Low and for the SK Mid. Where it's kind of a game and people can with like a joystick go through the area on the ground, but in the air also see things from space. So it's pretty cool. And each time we organize this exhibition also we try to have some events. And it's really about linking science and arts, because it's a very good way to transmit knowledge to public. If you ask public in the street, they don't have a good understanding of things. But if you put arts around, then they can be, there's some feeling that are probably easier to capture. Yeah, and because of that, we also created a movie. This movie is Archaeology of Light. You can see it on YouTube. It's both in 2D and 3D if you have glasses. And basically, it's a journey through the universe, through numerical simulation of the universe, and also through the SDSS data. And you can really, the movie is 20 minutes. I won't show the full movie here, but please have a look if you didn't know about it. And to finish, I want to mention two, channels for students if they want to come to Switzerland. We have basically, at least two ways. I mean, that's the most broad one I'm showing. We have this, what we call the Swiss Government Excellence Scholarship. This is both for PhD students or postdoc visits or research visits. There's a yearly application, typically end of November, and you basically have to send the application to the Swiss Embassy in Pretoria. I mean, there's a link, but you can just Google it and you find it. And those are, good way for, people all over the world, not just at South Africa, but to have, visit in academia in Switzerland. We also run just at EPFL a program which is called Excellence in Africa. One of the program is a PhD program. Up to now, there's 40 PhD studentship that has been awarded 2022 and 2024. and ultimately there will be 100 of them. There's a next call for another 20 PhD studentships that will gonna open next year to start in 2026. There's also some other program like the Junior Faculty Development Program, which is kind of an ERC grant given to a junior professor in a African institution. And for your knowledge, this program is basically funded by a very rich donor in Morocco, who really is keen to develop knowledge and excellence in Africa. And they basically ask us EPFL to run the program. So and to help people in developing for excellence. And that's it.
Yes, so any questions? And thanks for John Paul again. So I have some questions about the robotic arm.
Oh, yes, yeah.
So this, when you have a during observation run and you put and let's say you one of the fibers is a bright galaxy, so does the system check that the redshift acquisition was successful, and can the robot change the fiber to another target on the fly, or
no?
You cannot do that.
No, because it's really you design your observation well before doing the observation. And you will not adapt your observation depending on what you're getting. Because you basically spend a minimum of 10 or 20 minutes on target before being able to do a measurement. And the data rejection is not like instantaneous. So it will take like 10 minutes or so. So you cannot really adapt. What you can do, on the contrary, is like, if, for example, there's like a supernova explosion somewhere and you're interested to take a spectra and it goes in your field of view, you can adapt your strategy of observation and just basically move that fiber which is close by to that transient object. But you don't do that during the observation. You always plan beforehand.
Okay. And the fiber collision, so this was a problem with SDSS when you want to do halo patient studies.
Yeah.
So this is better now.
Yes, it's not completely, I mean, it's better because your system is smaller. So the collision fibers, it's on a smaller region, but it still exists. But what's gonna happen with even in DAISY or in the next generation survey is you spend not just one exposure on a given part of the sky, but multiple exposure. So then you can remove this collision problem because you have many exposure at the same location.
Okay.
And typically for DAISY, we're taking 5 to 7 exposure at a given location, and other survey will be similar in the future. So ultimately, the galaxy, fiber collision will kind of disappear in the long term.
Okay. How long is this long term?
Well, it's almost disappearing in DAISY. So after a couple of years of observation, when you revisit your field, then basically you remove this collision. Not completely, of course, especially if you're in a very dense region. But if you do cosmology, you're, less interested to the dense region. Of course, that will change with the new facilities, but also the fact that you have a much larger density of fibers also will remove this effect.
So about the interaction, now going to the beginning.
Yeah.
So when interaction of that matter with the structure with the galaxies.
Mm-hmm.
So sometimes when you have radio images, you see that the jets somehow are twisted, or they look they are doing some work against the structure or something.
Yeah.
So what are your thoughts on that?
Well, I think there's two things. It's either It's coming from the assembly of a galaxy, matter falling onto a galaxy. It's not, I mean, a galaxy plane is very straight and very thin, but the environment is not at all homogeneous. So your galaxy plane has to deal with, the environment. And so the angular momentum may be change a little bit, depending on the surrounding. And also all smaller units, smaller galaxy, will fall onto the big galaxy, and they can create this warping effect.
Do you have any thoughts on this result on dark energy being evolving or dynamic?
Yeah, it's a good question. I think I would say it's a bit early to say. In terms of data, no, we collect 3 times more data, but nobody, because of this blinding, we don't know exactly what's going to happen.
Right.
And the blinding hasn't been removed. But in a couple of months, we have a much clearer idea what happened.
It looks like that first, like that Redshift 0.5, but there's something
Yes.
going on there.
Yes.
And do you think this could be affected by like nonlinear, like baryonic effects, or?
That's possible.
Yeah.
Yeah. I think there's still a lot of unknown in this measurement.
Okay.
But of course, it's it's interesting.
Yeah, it's interesting. Yeah.
Whether it's dark energy, evolving dark energy, or it's something else, it will tell us something interesting. But I think it's good that you don't find always lambda. model,
No, it'd be great.
So, and maybe it's also linked, with the other problems we have in terms of Hubble tension or sigma heat tension. Yeah, maybe, and hopefully, this tension will disappear, and then we have a better understanding of cosmology.
Yeah.
Following questions.